Good afternoon. Today I will summarize the paper and improved FPTS for 01 knapsack by Seijin. 2019. The presentation explains what the problem is, the paradox bounds for fully polynomial approximation schemes, in short FPTS, and the new algorithmic technique introduced by the paper that improve the dependence on the approximation parameter epsilon. My aim is to give you an intuitive understanding of the ideas, greedy decomposition, and the Mark-Ilvan number theory construction, and using subset sum FTS and fast convolution building blocks. So now coming, care why do we care about the faster FPTS for knapsack? The 01 knapsack is everywhere in algorithms and applications, and an FPTS gives an guaranteed 1 plus epsilon approximation where runtime grows in polynomial in n and 1 by epsilon. For practical and theoretical reasons, we want the runtime to be nearly linear in n and have the exponent on 1 by epsilon as small as possible. Progress here often combines combinatorial insights and speed up for convolution-like operations. The paper pushes that boundary by lowering the exponent for 1 by epsilon in the deterministic setting. The problem statement formally here we give it an item, profits pi and weights wi and capacity w. We seek a subset whose total weight is at most w, while maximizing total profit, and FPTS returns a value v such that uh, v divided by v is less than optimum. V is less than or equal to optimum, less than or equal to 1 plus epsilon multiplied by v. This paper follows a common reduction used in earlier work. Rescale the problem so the item profits lie in range of 1 to 2. By grouping profits by magnitude, then approximate the entire profit function f of x, which maps capacity x to the maximum achievable profit with that capacity. To multiplicative 1 by epsilon, 1 plus epsilon's accuracy working with the whole function enables first divide and conquer merges. The prior FPTS bounds basically was the historically Ibarra and Kim and Lawyer gave early FPTS with polynomial time of O of n log n plus 1 plus e 1 plus epsilon to the power 4 times logarithm of 1 divided by e. Then the latest work by Chan in 2018 gives us the time of O of n plus 1 by epsilon to the power 12 plus 5 divided by 2 to the power omega into square root of logarithm of 1 by epsilon. It has used the number theoretic rounding plus fast convolution primitives to get the polynomial timing. This paper improves chance exponent from 12 by 5 to approximately 2.4 to 9.4 to 2.25, still having some subpolynomial that gives us the time of n plus 1 by epsilon to the power 9 by 4 divided by 2 to the power omega times square root of logarithm of 1 by epsilon. That's actually proved exponent. So the exponent on 1 by epsilon is reduced. That's a meaningful asymptotic improvement approaching a non-conditional lower bound link to the minimum convolution problem. Now coming to the main results, this paper states two main theorems. First, a deterministic 1 plus epsilon approximation in O of n plus 1 by epsilon to the power 9 by 4 divided by 2 to the power omega square root of logarithm of 1 by epsilon. The second for the regime where the n is equals to 1 O of 1 by epsilon, its bound the bound improves the further. The big picture, the new algorithm combines three ingredients: a greedy partitioning to reduce work on a cheap item, a multi-level number theoretic rounding constructions called a set tower to sharply reduce distinct profit values to handle, and fast merging of profit functions via divide and conquer plus SMAWK or other convolutional speedups. The high-level overview of this algorithm is basically in the step 1 we use the standard reduction to group profits into geometric classes and the reduce and reduce each group to the case pi in the range of 1 to 2 range, and the in the step 2 we sort the we sort we sort by unit profit pi divided by w and split into HML sets. The H contains the top uh, omega of 1 by epsilon highly profitable items. The L contains item with unit profits far below H. M is the middle. Step in the step 2 process H, M and L differently. Greedy handles the H. M is handled by rounding the unit profit to small discrete and applying the multi-level scheme. And the L is cheaper to the approximate because lemma bounds total profit contribution of L in any solution of interest. The step 4 we are merging the per group profit functions using fast max plus convolution uh, function primitives to get the global approximate function and evaluate the W. In the greedy split, H or M or L, why do we use actually split? If many items are extremely good by unit profit, you can capture most profit by looking only at the top of O of 1 by epsilon once the H basically. The paper proves a greedy lemma when H is the top, where B is equals to omega of 1 by epsilon naught items. The L are items with unit profit less than 1 minus alpha times the minimum in H. Then in an optimal solution of interest, the total profit from L is bounded by omega of epsilon to the power minus 2 by 3, or in the tuned final analysis by a quantity that makes cost favorable. Practically this means we only need to approximate L up to a small relative bound P prime rather than the full scale, which reduces time, and M is treated by rounding unit profits into powers of 1 plus epsilon. So there are few distinct values. These groups are assembled via subset sum FPTAS kernels. In the multi-level set-toward idea, a core novelty, Chan used a number theoretic construction mapping profits to multiples of a small set delta. Jin extends this to multiple levels, building delta 1, generate delta 2 from small integer multiples of delta 1, continue up to delta d. This tower ensures that at higher levels we can represent many profit values using multiples of a small top set of delta d while controlling the additive rounding error. The multi-level idea lets you trade off how many distinct unit profits remain at each stage and compute small additive approximation quickly. This is what lowers the exponent from 12 by 5 to 9 by 4 after carefully tuning parameters. Now coming to the merging via max plus convolution. After finishing HML, M and L separately, we have monotone step functions representing achievable profit versus capacity for group. Merging them as max plus convolution, the algorithm uses divide and conquer merging and accelerates inner steps using SMAWK when the involved functions have zero concave structure. This is how Chan achieved super polylog speed ups. The partitioning and the multi-level rounding reduce function complexity so that the merge cost overall yields the improved exponent on 1 by epsilon. Now coming for the complexity sketch and takeaways for further direction. In sketch, greedy splits cut down the heavy work on L, multi-level rounding reduce distinct profit values, and the work per merge. Fast convolution technology gives further subpolynomial improvement, and the result is stated of n plus 1 by epsilon to the power uh, 9 by 4 divided by 2 to the power omega and square root of logarithm of 1 by epsilon runtime. The takeaways explains mainly the paper demonstrates how combining number theory and greedy structural lemmas and advanced convolution techniques can subtly but meaningfully improve the polynomial dependence on 1 by epsilon. Open directions remain. Can the exponent be pushed to 2, the conditional quadratic barrier, or can constant log factors be improved further? Thank you.